Thank you for the kind introduction and thank you for the invitation. So this talk will kind of have two separate parts with a pause in the middle. The first part is really about the physics of gravitational wave astronomy, why we're particularly interested in asymmetric binaries, and just touching a little tiny bit on modeling. Then the second part will be more technical details about how we do this modeling using black hole perturbation theory and gravitational self force. Okay, so there's quite a few subheadings here, but big picture, what are asymmetric binaries? Why are we interested in them? How do they fit into the overall scheme of gravitational wave astronomy? How do we model them? Then I'll take a little bit of a detour into how this work relates to the equivalence principle, and then getting more technical into how we actually do the concrete calculations. Okay, so starting off with just gravitational wave astronomy. Now, I've just heard that you have already had, or in the middle of, a course on this topic, but just to segue into it, why is gravitational wave astronomy so interesting when we already have conventional electromagnetic astronomy that already lets us have beautiful pictures like this? I really should have updated this. This is Hubble. Of course, now we have more recent pictures from James Webb. So we already get a lot of information from conventional astronomy, but a lot of the most dramatic, most energetic events in the universe, we actually just don't see at all with conventional astronomy. So in particular, black holes, we cannot get that much information about using conventional astronomy. So we think most strongly gravitating systems in the universe are well described by Einstein's theory of gravity, GR, general relativity. But until recently, GR has only really been tested in weak gravitational fields, like the solar system. There hadn't been a lot of strong tests of gravity in strong gravitational fields. And the regions of the strongest gravitational fields, like around black holes, we just really couldn't observe them at all with conventional electromagnetic instruments. Of course, we did get a lot of hints. We had a long history of seeing X-rays emitted from galactic cores that suggested there were massive black holes at the centers of galaxies. Then we had more direct observation of black holes at the center of galaxies. So this is a beautiful movie I always like to show. This is a time lapse movie showing stars in the center of our galaxy orbiting around something that you just can't see. It's black, it's invisible. And so that something is Sagittarius A star. I'll just keep that running a bit. Sagittarius A star, which is a massive black hole, or at least I'm pretty sure it's a massive black hole, weighing about 1,000,000 solar masses. So we did have amazing observations like this, and we were able to even trace out the orbits of stars around some invisible center. Here it's not invisible, it's just been colored by hand, but in the actual observations, we cannot see it. Then more recently, conventional astronomy gave us even better views of black holes, two black holes in particular, one at the center of our own galaxy and one in a neighboring galaxy, M87. So here, it's same story. We don't actually see the black hole. What we see is stuff around the black hole. So this is gravitationally lensed light emitted from plasma orbiting around the black hole. I think this is M87 rather than our own galactic core, but I don't actually remember. So these images came out from the Event Horizon Telescope, which basically turned the entire Earth into a gigantic telescope in order to get very precise angular resolution of light coming out of the neighborhood of the massive black hole. So with conventional astronomy, we are getting better and better views of what we think are black holes, but really these are still putting very, very mild constraints on whether GR is the correct theory of gravity, or whether these black holes are what we think are black holes as described by GR. And for measurements like this, it's really dominated by astrophysical uncertainties about the plasma orbiting around the black hole. So currently, we still don't get that much information about black holes from conventional electromagnetic observations. Now, that all started to change in 2015 when we started actually seeing, well, not seeing, more like hearing, um, gravitational waves emitted from compact binary coalescences, which are almost all black hole mergers. So I suspect you've all seen this picture before or something very similar to it. This was the first detection. Blue is the actual gravitational wave strain data, cleaned up a little bit. Then black is the theoretical prediction of what we expect the waveform to look like when emitted from a binary system like this of two black holes that were roughly equal mass and a roughly quasi-circular inspiral. So this is the general evolution of all binary coalescences. They start off with an inspiral, they lose energy, they get closer and closer together until they finally merge. Then you're left with a single object that's kind of vibrating with a very particular frequency that rings down into a stationary state. You get a waveform corresponding to that. So this was amazing. This was the first direct detection of gravitational waves. It was the first detection of black hole binaries. It's starting to give us more precise information about the population of black holes in the universe and the properties. So this was amazing. This, of course, earned a Nobel Prize. But nowadays, we see these things all the time. Here I'm showing just the signals from the first two observing runs of LIGO and Virgo. So these became pretty much everyday events. Back during these two observing runs, it wasn't every day, but quite a lot of events we saw. They all look pretty similar. Now, this is a public alert database that anyone can go look up, gracedb.ligo.org. So here you actually see in basically real time, within a very short time, you see each alert of a detected gravitational wave. You can see the most recent one is the 11th of October. This is just because LIGO is not currently taking data. But you see before that time, there were detections or possible detections almost every day. Some of these are likely or less likely to actually be real events. So this is a false positive rate of 1 per year or 1 per 2 years, but this one's 1 per every 30 or 10 to the 33 years or 10 to the 26 years. So we now see these things all the time. Using gravitational wave astronomy, we're now getting a load of information constantly about the population of black holes in the universe, and about their properties. And of course, we're also observing neutron stars and getting a bit of information about them. But the vast majority of all the signals we've detected are black hole binaries. But still, that's just stage one. We're going to be seeing a lot more in the future. So currently operating, we have two LIGO detectors. We have Virgo. We have the old Geo 600, which is still running, but was never even had the design sensitivity to detect anything. It was just demonstrating technology. But we do have three detectors actively collecting data and observing things. Kagra has been running and joining the observing runs, but it hasn't yet reached design sensitivity, so it hasn't yet actually directly detected anything. Sometime in the next 10 years or so, a third LIGO detector is supposed to come online in India, and then we'll have pretty good coverage of the globe. That's still kind of current generation 2G detectors, second generation detectors. Going further into the future, into the 2030s, we're expecting much more advanced detectors, in particular LISA, the space-based detector. So this is outer space rather than on Earth, which means it doesn't have all the kind of gravitational noise that you have on Earth. And all that gravitational noise, which coming just from gradients in the gravitational field, that's all kind of low frequency, which means that LISA will be able to see much lower frequencies because it doesn't have that noise. LISA is now in preparation. It's fully funded. Everything is kind of developing as we go. It was formally adopted earlier this year, and the expected launch date is 2035, so about 10 years from now. There are also a whole bunch of other projects in development. Daisago is a Japanese detector, also in space. That one, I think, has kind of lost momentum and is definitely not progressing towards being fully funded, but I think people are still actively pursuing it. Then there's two more space-based gravitational wave detectors in development in China. Probably just one of those will ultimately be supported, but right now they're both being actively developed. Then there's two ground-based detectors, which are called third generation ground-based detectors, which will be about an order of magnitude more sensitive than the current detectors. That's Einstein Telescope in Europe and Cosmic Explorer in America. So once we have all these things running, we'll be able to see an amazingly vast array of different systems. So basically, we can see all black hole binary mergers over the entire history of the universe once we have this array of detectors up and running. We also have much greater precision when we observe the same kind of signals we currently observe. And yeah, we'll see things much, much further away and fainter, which is what enables us to see everything in the past history of the universe. So this is the kind of the frequency spectrum of things we will see with different detectors. And if you're interested in gravitational wave astronomy, I highly recommend just playing around with this website, GW Plotter. There's an associated paper describing how they come up with the curves and everything. But the basic story is that the frequency of a gravitational wave, if you just use kind of Kepler's law to estimate the frequency for a given binary of orbital radius r and total mass m tote, the frequency of the emitted wave scales with the orbital radius and total mass in this way. And since these are highly relativistic systems, the orbital separation in geometric units is comparable to the total mass, which means that the frequency of the emitted wave is roughly 1 over the total mass, because you just get m total divided by m total cubed, square root that, and you just get 1 over mass. So what this means is the lower the frequency you can observe, the bigger the mass of the system you can observe. So we're currently detecting things with LIGO. That's this curve right here. That's the sensitivity curve. So anything above that we can detect. We're currently detecting things in roughly 100 hertz range, 100 hertz up to kilohertz. And that's why what we always see right now are things that are, a few solar masses or a few tens of solar masses and maxing out at around 100 solar masses. That's because this low frequency noise here, coming from gravitational gradients on Earth, it prevents us from observing heavier systems. So once you go into outer space with Daisago or LISA, you'll see much lower, or you're sensitive to much lower frequencies, which means you can see much heavier systems, which means you can start to see systems involving those massive black holes at the centers of galaxies, the kinds of black holes I was showing you pictures of at the beginning from the Event Horizon Telescope or from things orbiting around the center of our own galaxy. So there's two very interesting systems in particular we expect to see with LISA. and these are really kind of the most interesting systems we can see with LISA. These are called massive black hole binaries. That's when you have two galaxies merging, and then when the galaxies merge, the massive black holes at their center also merge. And so those will be by far the loudest, most powerful events in the universe. Then we'll see things that still involve a very heavy black hole, but also involve a small black hole or a small neutron star called extreme mass ratio inspirals. And that will be a big focus as we progress. Then if you keep going to lower and lower in frequency, you get into the pulsar timing array frequency band. So this is observing, rather than massive black holes, which might be 1,000,000 solar masses, this is observing supermassive black holes that are billions of solar masses, for example. And as of about a year ago, they're pretty confident that with pulsar timing arrays, they have now observed a background of gravitational waves coming from supermassive black hole binaries. Okay, so just a bit more about these different kinds of binaries. So what we currently see with LIGO, Virgo, Cagra are almost all comparable mass binaries, where the two black holes are roughly the same size and mass as each other. LISA will still see these same kinds of binaries, but everything will just be heavier. So you'll see two massive black holes merging rather than two stellar mass black holes merging. Or in principle, LISA can also see the same kinds of systems we currently see, but just much earlier in their evolution when the two bodies were more widely separated, and therefore at lower frequencies. Then you have systems called intermediate mass ratio inspirals. So for example, you could have a massive black hole in a galactic core orbited by an intermediate mass black hole. So say you have a 1,000,000 solar mass black hole at a galactic core orbited by a black hole with mass, say 1,000 solar masses, or 10 to the 4 solar masses, around there. So that would be kind of a heavy intermediate mass ratio inspiral where both bodies are heavy. That's what you'll see with LISA. With ground-based detectors, such as the Einstein telescope, you're more likely to see, or you're able to see, light intermediate mass ratio inspirals, where the heavier black hole is, say, 100 solar masses or 1,000 solar masses, and then it's being orbited by a stellar mass black hole that was just formed from gravitational collapse of a star. These systems, we don't know how many of these exist. We haven't observed any directly, but in principle, they're very, very interesting because either the larger or the smaller black hole will have to be an intermediate mass black hole, meaning it's not stellar mass, so it's not something that was just formed from gravitational collapse of a star. And it's not massive, meaning it's not one of these massive black holes that sit in the galactic cores of every galaxy, as far as we know. Intermediate mass black holes, we actually don't know how many there are. We've seen one that was around 100 solar masses that was the outcome of two smaller black holes merging. But we really don't know much about the population of intermediate mass black holes. If we were able to observe them, and especially if we were able to observe quite a few of them, then we'd get a lot of information about the actual evolution of all the black holes across the history of the universe. Because right now, we know how small black holes form. They form when a star collapses. We do not know how massive black holes formed. There are a lot of different conjectures, a lot of different possible explanations, but we really don't know. And so having something in between would tell us a lot. For example, it could tell us, are massive black holes formed when just you have a series of mergers? So multiple, say you have two stellar mass black holes merging to form an intermediate mass black hole, and then you have two intermediate mass black holes merging, or intermediate mass black hole absorbing a smaller black hole on the way to becoming a massive black hole. So these will really be crucial ingredients in our understanding of kind of the demographics and evolution of black holes across the whole history of the universe. Then you have these most extreme systems called extreme mass ratio inspirals, or EMRIs, that Esteban noted at the beginning, or mentioned at the beginning. So these, because your smaller object, your smaller black hole or neutron star, is always going to be, around a solar mass or heavier, to have a really extreme ratio of masses, you're going to need the larger object to be a massive black hole. It's going to have to be 10 to the 5, 10 to the 6 solar masses. Now, these systems are very, very interesting, and they're key sources for LISA because they have very specific features that you don't get with any other systems. So in particular, this smaller object orbiting around the big black hole spirals in quite slowly, which means you see a huge number of cycles, a huge number of orbits, basically proportional to the large mass ratio. So meaning large mass over small mass. So if you have a mass ratio of 1,000,000, you might have 1,000,000 orbits within the LISA band. So during that slow inspiral, typically these orbits are also very, very intricate. I'll show you a lot of examples later. They're not simple ellipses or simple quasi-circular orbits. They're very complicated. And so you can kind of think of the smaller object tracing out all of the space-time around the large black hole. And because of that, you have a ton of data in the waveform that comes out. You have a ton of data about the system parameters that generated your waveform. So you can get a ton of information about the large black hole itself. Typically, the information you can get about that is orders of magnitude more precise than with any other experiment. But you can also get a lot of information about the environment surrounding the large black hole, which means you're able to probe galactic cores where these massive black holes reside. You can learn about what's the population of other bodies in the neighborhood. You can learn more about what are the properties of accretion disks, etc. Okay, and to give you a sense of scale, I'll show you just a snapshot from that movie I showed earlier. So here was that little star orbiting around some black hole that you can't see right here. That star, the star that comes closest to the massive black hole, at its closest approach is around 200 Schwarzschild radii. So roughly 200 times the size of the massive black hole. And kind of think of the scale of that. So Sagittarius A star is about 1,000,000 solar masses, which means it's 1,000,000 times heavier than our own sun. But in terms of just spatial size, it's basically the same size as our sun, which is huge. Our sun is gigantic. And this is at closest approach is about 200 times that scale away from the black hole. Now that contrasts with EMRIs, where you'd have to zoom way, 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 way in to a smaller scale than you can even see to actually see this system. So this small object, like I said, traces out this very intricate orbit, and you get about 10 to the 4 or 10 to the 5 cycles, or 10 to the 5 orbits, within 10 Schwarzschild radii. So a factor of 20 closer than the currently closest star we can see. So this is why you get like incredibly precise measurements of the neighborhood of the small black hole, or sorry, of the large black hole. Okay, so say we observe these things, what do we learn? One of the most interesting things we can start probing is this thing called the no-hair theorem of GR. So in GR, all black holes that are, approximately stationary, that are sitting there in isolation, all black holes look almost exactly the same. They all have a unique shared form that they share between them, which is described by the Kerr metric. They're all Kerr black holes. A Kerr black hole is specified by only two parameters, its mass and its spin, which means that no matter what happened to form this black hole, no matter what its history was, no matter what has fallen into it, as long as it's sitting roughly in isolation and it's settled down from whatever, violent events happened in the past, it's always specified by exactly two parameters, mass and spin. And one thing that means is that all its higher multipole moments, its quadrupole moment, its octupole moment, etc., are all uniquely determined just by its mass and spin, which is totally different than any material object we can think of, where every multipole moment describing its shape is freely specifiable. You can keep specifying the quadrupole independently of the mass, you can specify the quadrupole independent of the spin, etc. So this is one of the kind of most profound predictions of GR, that all stationary isolated black holes are almost exactly the same, no matter what has happened to form them or no matter what has happened to them. Now, what we don't really know yet is whether the black holes in the universe are actually described in that way. We do not yet have enough precision to test whether the black holes that we think are out there are actually described by GR's prediction that they are the Kerr black holes. So if we get measurements of these emeries with Lisa, we can actually start testing that with, many digits of precision. So we can actually test whether black holes are well described by what we think they should be well described by, which is the Kerr geometry. And yeah, emeries will provide tests that are vastly more precise, tests of this very specific thing that are vastly more precise than any other tests. Okay, well, we can do more. So with emeries, we get information about fundamental physics, astrophysics, and cosmology. So I mentioned measuring deviations from the Kerr geometry. So we do that by measuring the black hole parameters, its mass and its spin. We'll probably be able to measure that to at least 0.01% precision. And separately, we can measure the quadrupole moment and see, is it described by the Kerr formula that tells you how the mass and the spin relate to the quadrupole moment. So we'll get very, very precise measurements of that. Well, we can also do broader tests of fundamental physics. We can search for new fundamental fields. So, most theories that try to unify gravity with particle physics would say that, some scales in strong gravitational fields, you will have new fields appearing that are not the known fields. So, for example, new scalar fields that are not Higgs bosons, there's some other scalar field. And emeries and emeries as well, will give us a good way of looking for that, if in fact that is occurring in the strong gravitational fields and galactic cores. And you can write down many, many tests of GR that you can do with emeries. You probably get, I don't know, one paper every few days on that appearing. Okay, then you can also do astrophysics. So basically, you can measure, just by measuring the mass and spin of massive black holes and of the smaller black hole, you get a ton of information about black hole demographics. So in particular, you constrain the mass function, telling you about the number of black holes across the universe with any given mass, which tells you about the history of black holes, the formation channels, etc. We also know or expect that there are large dark matter halos surrounding massive black holes. And it's possible that those halos form sharp cusps very, very close to the massive black hole. And if they do, then measurements of emeries can possibly constrain or rule out different models of dark matter. As I mentioned before, you'll also be able to measure the surrounding environment, not just dark matter, but if there's an accretion disk, you can measure properties of the accretion disk. You can measure presence of nearby bodies to get more sense of the population of bodies around galactic cores, etc. And if you measure a whole bunch of emeries, and in fact, we really are hoping to measure a whole bunch of emeries in order to help us distinguish between fundamental physics effects and astrophysics effects. If we just measure one emery, it might be very hard to distinguish something that's coming from a new fundamental field versus something that's coming from an accretion disk, for example. But if we measure quite a few of these, then we can also start doing cosmological measurements by using emeries as standard sirens. And it's expected we will be able to have an independent measurement of the Hubble constant to around 1% accuracy, which may not be totally competitive with other cosmological measurements, by 2035 or 2040, but because it's a totally independent measurement, it might help with the Hubble tension that we currently have, where we have conflicting, contradictory measurements of the Hubble constant. So measuring emeries, observing emeries with LISA will, reveal this treasure trove of science.
Oh,
The best estimate of the number of signals, emery signals we will see, is in the low hundreds. We'll probably see 100 or 200, somewhere around there. Emery signals during LISA's lifetime. For these fundamental physics tests, you're really hoping for loud emery signals with high SNR, and we're hoping to see just maybe a dozen or a few dozen of that kind of system.
Is any chance to say something about primordial black holes based on this?
Yeah, you could have primordial black holes orbiting an intermediate mass black hole, for example. Primordial black holes orbiting a massive black hole, because the mass disparity is so big, you won't get a lot of evolution during LISA's lifetime, which makes it harder to do interesting science. But yeah, you can have primordial black holes or light objects like brown dwarfs potentially. It would also form emery type systems.
Okay.
Okay, so that is why we are interested in these asymmetric binaries. So asymmetric binary just means you have a mass asymmetry. One mass is much bigger than the other. That's why we're interested in them. Now let's start talking about modeling them. Okay, why are we even talking about modeling them? Well, hopefully you've seen from the lecture course on gravitational waves and I guess post-Newtonian theory. We need theoretical waveform models for two reasons. One is, very often we would not even be able to find gravitational wave signals in the data without models. That's actually the typical scenario. If you just look by eye at the data, it's just a jumble, you don't see anything. So you really need to know what you're looking for, which means you need many, many, many models of potential possible observable waveforms, and then you go looking for those in the data. So that's one issue. Finding the signal, detecting the signal requires models to begin with. Another issue is, say you find a signal using whatever method, maybe you don't have a model, you find a signal some other way. The signal by itself is totally meaningless until you have a model telling you how a given signal relates to a given source. And so for that, you need not just a picture of what a waveform looks like, you need to know kind of a mapping between binaries, specific black hole binaries or whatever, compact binaries. You know exactly how a given compact binary relates to a given waveform. And so for that, you need theoretical models. And the way you get them is always basically the same. You solve Einstein equation. So here I'm writing the Einstein equation for some metric G with some stress energy source T. Depending on how you're doing the modeling, you might not have a stress energy source in there at all because black holes actually don't have any stress energy. They're just vacuum. But this is just the generic structure. Einstein tensor equal to stress energy tensor. So you want to solve this system of equations, which is typically called highly nonlinear. It's a highly nonlinear set of coupled PDEs that are of mixed hyperbolic and elliptic type. So it's a very complicated system. You want to solve this system or solve the system of equations for a physical system containing two compact bodies orbiting each other with boundary conditions specifying there's no incoming radiation. So the system, the orbiting bodies are the ones creating all the outgoing radiation. No radiation is coming in. Now, once you've solved this equation, you can just read off the metric at large distance away from the two bodies, and that gives you the waveform. You just read that off. And now, because you've solved the Einstein equations throughout the entire space-time, you can then say, how does that waveform relate to the source that created it? And that gives you a way to identify, if you found a signal in your data, what created it. And that's what enables you to actually do science and do all these tests of fundamental physics and all these astrophysical measurements and so on. Now, I'm going to be talking about modeling asymmetric binaries, but I'll start off with kind of the standard picture of how we model current signals detected by LVK, LIGO Virgo Cagra. So this is a picture from Luc Blanchet of kind of a typical waveform and what you use to model it, each part of it. So you start off with post-Newtonian theory, which, as I understand, you're learning all about. So they're basically the two objects, the two black holes, are starting far apart. So you have relatively weak gravitational fields, relatively slow velocities. And so then you can approximate Einstein's theory of gravity as an expansion around Newtonian gravity. That's post-Newtonian theory. And that describes the in-spiral phase until you get into the deep, strong field. And so meaning once the two bodies are very close together, then post-Newtonian theory stops being accurate. And then you really rely on numerical relativity, where you are solving the fully nonlinear Einstein equations on supercomputers, letting your computer run for weeks or months to model just a single system with a single emitted waveform. Then once your two objects have merged, then you have just a single black hole that, as I mentioned earlier, is just kind of oscillating with very characteristic frequencies, settling down to a stationary state where it's well described as a Kerr black hole. And so for that last little bit, you basically have a Kerr black hole plus small perturbations. And so it's well described by black hole perturbation theory. So here's the outcome of a numerical relativity simulation. This is the kinds of systems we typically focus on currently, where there's not a huge difference in size and mass between the two bodies. The motion is almost perfectly circular. It's quasi-circular. Everything is quite simple. But that's really focusing on a very specific part of the binary parameter space, the two-body problem parameter space. So if you're thinking of the two-body problem, you have two most important parameters. You have the orbital separation, how far apart are the two bodies, and you have the mass ratio. How big is the larger body compared to the smaller body? So the kinds of systems I just showed you that movie for, and Luke's picture of the typical waveform, that is very focused on this regime over here, where the two bodies are roughly equal sized. And typically with ground-based detectors, the orbits are also very, very close to circular. And in fact, numerical relativity spent many, many years and still works hard to eliminate eccentricity from the simulations to make things as circular as possible, because that's what we think most systems that we currently see exhibit, almost perfect circularity, because they've already kind of dissipated away eccentricity by the time we see them. So we are currently, the community is very focused on particular kinds of systems, comparable mass binaries, and quasi-circular configurations. So in that case, you have, when they're widely separated, you have post-Newtonian theory, as I mentioned. Then as you lose energy through gravitational wave emission, you kind of move down on this diagram until you have to use numerical relativity. Then the two objects merge, and you're still using numerical relativity, or you can use black hole perturbation theory for the last bit. And then there's a whole paradigm of stitching these different models together, because numerical relativity, as I said, takes weeks or months to generate individual waveforms, whereas you need to be generating millions or billions or many more than that waveforms when you're doing gravitational wave data analysis. So you then have to build a fast model on top that combines post-Newtonian information with numerical relativity. But this whole paradigm is very focused on this left half of the diagram. Whereas what I'm interested in for these asymmetric binaries is the right half of the diagram, where one object is much heavier than the other one. And these kinds of systems are going to be most interesting for next generation detectors, in particular LISA, and to some extent, third generation detectors like Einstein Telescope and Cosmic Explorer. But even with LIGO, Virgo, Cagra, we're already detecting fairly asymmetric binaries. So the most asymmetric one we've observed is a mass ratio 1 to 25, which may not seem like a very extreme mass ratio, given that I was talking about 1 to a million before. But as far as numerical relativity is concerned, that's a pretty extreme mass ratio, because numerical relativity really cannot handle large mass ratios. So we already have a need to start working, not just start, we already started decades ago, but to put more and more focus on this regime down here, which is strong, strong fields. The two bodies are close together, but asymmetric masses. One body's much bigger than the other. Now, so I showed you a typical waveform that we currently see with LIGO. Here's what we are more likely to see for a very asymmetric binary. So it's not just a simple sinusoid, it's very, very complicated. These are the two polarizations, H plus and H cross. They look nothing like each other, but they're also very, very complicated individually. And here what we're seeing is really kind of beating phenomena between many different frequencies. And you in fact have three base frequencies and then all their harmonics, and they're all beating against each other, giving you this complicated pattern. And they're evolving with time. So this particular system is mass ratio 1 to 1,000. So that's kind of an intermediate mass ratio. Eccentricity 0.22. So if you don't remember your Keplerian dynamics, eccentricity ranges between 0 and 1 for a bound system. And so this is moderate eccentricity. This is very, very eccentric for typical LIGO systems. This is like incredibly eccentric for typical LIGO systems. But this is kind of actually on the medium or lower end for MREs, for example, or what we expect. We don't really know what the distribution of eccentricities is going to be. And this is for the larger black hole spinning with a spin of 0.7. And so spin for a Kerr black hole ranges between 0 and 1. So this is on the kind of moderate range. This would be probably on the high range for things we can see with ground-based detectors, but actually probably on the low range for MRIs, where a lot of X-ray observations predict that massive black holes have really high spins of like 0.9 or higher. Okay, so the waveforms look way more complicated for these systems, and the systems themselves look way more complicated. So this is a quite old movie of a MRI evolution. I think this is a mass ratio 10 to the 5. And that sound you're hearing is actually, some multiple of the actual gravitational wave frequency. So if you compare these kinds of incredibly complicated systems to the quite simple quasi-circular equal mass systems I showed earlier, you can get a sense of why a totally different modeling technique is required. You might have noticed that during this evolution, the central black hole, shown here in this gray blob, seemed to be getting bigger with time. That is not actually happening. This is just the movie zooming in closer and closer to the black hole. This was actually created almost 15 years ago, I think, and the model that was being used is not that accurate, but qualitatively it's right. This is qualitatively what everything will look like. Okay, now I will get into how we do that modeling in some detail, hopefully not too much detail, in the second half of the talk. But I first want to take a short detour into how it relates to the equivalence principle. So in the title of the talk and in the this two-body phase space diagram, there's this mention of self-force as the method in which we use to model these asymmetric systems. And so we'll talk a little bit about what that means in terms of the equivalence principle. What is self-force and how is it related to the equivalence principle? So the basic idea is we're doing some kind of perturbation theory, some kind of approximation, where we say we have some background spacetime. In the case of an MRI, that would be the larger black holes spacetime, treated as if it were in total isolation, not affected by the presence of the secondary small object. That would be this metric here. So that would be, for example, the Kerr spacetime metric. Then you have small corrections coming in due to the finite mass ratio. So I'll use epsilon to denote small mass over big mass. So you have all these perturbative corrections. Back up. So the total spacetime is spacetime of the big black hole plus corrections. Now, self-force theory isn't restricted to MRIs. It's always applies when you have a small object in some ambient spacetime. And the key thing is this finite mass and size of the small object is changing the geometry around the small object. And that change in geometry is actually reacting back onto the small object, changing its motion. It's exerting what we call a self-force. So you get these small little corrections to the geometry around the object. That small change influences the object's own motion. And then you get an equation of motion that looks like this. So on the left-hand side, this is the covariant acceleration in the background metric. So I trust you've all seen the geodesic equation in the introductory GR lectures. So if the motion were exactly geodesic in the background metric, in this little g here, you'd have exactly 0 on the right-hand side. You'd have 0 covariant acceleration. That's the principle that in gravity, you normally would say, okay, you don't have a gravitational force. Things are just moving on geodesics determined by the geometry. What this is saying is that that's an approximation. The idea that things move on geodesics, that is a test particle approximation. That's the approximation where you're saying the object is sufficiently small and sufficiently light that you can neglect its impact on the geometry around it. And in that approximation, it then moves on a geodesic of the external ambient geometry. Now, when we're doing self-force calculations, we are finding the corrections to that principle. Order by order, we are finding this very tiny corrections to the geodesic principle. And depending on who taught you GR, sometimes you'll hear that the geodesic principle, that test particles move on geodesics, sometimes you'll hear that that's a hypothesis of GR. You'll hear that you assume that to be true as part of the assumptions of GR. But in fact, that's not true. In fact, you can prove that's true. Sorry, you can prove that sufficiently small, sufficiently light objects move on geodesics of the external geometry. Not only can you prove that, you can calculate explicitly what the corrections are. Okay, so how does that relate to the equivalence principle? So here I'm going to go way back to basics that you should have seen when you first learned about GR. So GR, is describing gravity as a manifestation of space-time geometry. This is kind of a classical rubber sheet analogy where you say, okay, if I put a heavy object onto a rubber sheet, it deforms the geometry of the sheet, and then that geometry dictates the motion of nearby objects. So if you just release that little body here, it falls in because in this analogy, you're saying the object is confined to this surface, and basically the geodesic principle is dictating that it's moving down along this curve as you would expect a real ball to do on a rubber sheet. Or if rather than releasing it from rest, you give it a little kick, then it'll orbit around, in this case on a circle, and that again is just a geodesic of the geometry determined by this heavy sun in the middle. Now, the equivalence principle, again, depending how you learned it, one variation of the equivalence principle is the statement that a freely falling observer measures the same things as an observer moving at a constant velocity in flat spacetime. So, say you just release an astronaut, an observer, let him fall in, and he sees this orbiting little object. Then in this little vicinity here, spacetime is approximately flat. Take a little bit of spacetime, it looks flat. And the equivalence principle is saying, okay, zoom in very close into a very small region. All freely falling test particles will move like they would in flat spacetime. Because this observer is supposed to see things exactly like an inertial observer in flat spacetime. And test particles in flat spacetime move on straight lines. That's what a geodesic is in flat spacetime. And then the generalization of that is that in this little tiny patch, you don't see any covariant acceleration of this orbiting body. Basically, it's locally a straight line. And that's the concept of a geodesic. So the equivalence principle is saying, okay, locally, free-falling things look like they're moving on straight lines. And that means that they're moving on geodesics, and that's the geodesic principle. Now, let's look at our context. We've got, say, a massive black hole at the center of a galaxy. So rather than having a sun doing the deforming of this rubber sheet, we now just have a big hole. It just gets steeper and steeper and steeper. And if an object is sufficiently far in, it doesn't matter how much it tries to accelerate its way out, it can't get out. Then we've got a little object orbiting around. And what we need to do is account for the very small correction to the geometry due to the presence of this small but finite object. So that deforms the geometry in its neighborhood, and that influences its motion. It's no longer moving on a geodesic of the external geometry. So we're really looking at corrections to the equivalence principle, or at least to a certain variation of the equivalence principle. So again, this isn't something that just happens in MREs. This happens all the time for every object, everywhere. All objects experience this little self force. But in most contexts, it's so tiny you couldn't possibly measure it or care about it. So for example, if you had an astronaut orbiting around Earth at reasonable distance, like at the space station, International Space Station, that astronaut will experience a self force due to his or her own influence on gravity around him or her. But that self force is roughly 1/trillionth of 1/trillionth of the astronaut's weight. So you can't possibly measure it. There's all the other possible little effects around you are much bigger than that. Now, in an MRE, the effect at a given instant in time is still tiny, really, really tiny, because it's of order the mass ratio. So if your mass ratio is 1 over 10 to the 5, or 1 to 10 to the 5, the magnitude of the self force is very tiny. But that tiny effect accumulates over this long inspiral lasting 10 to the 5 orbits and ends up having a huge impact. It's what actually causes the small body to spiral towards the big body. So it's what causes the eventual merger of the two objects. So to detect an MRE and extract information about the massive black hole and about the surrounding environment and everything, the goal is to very accurately model this tiny, tiny correction to the equivalence principle, model that for potentially hundreds of thousands or millions of incredibly intricate orbits. That's the objective. Okay, we're at halfway through, and that is where I planned to take a short break. So I might just grab a little bit of water, and
This meeting is being recorded.
okay. Okay, so far it was kind of big picture, non-technical stuff. In the second half, I will get much more technical, but hopefully not too technical, and talk about how we actually do these calculations, how we get the waveform, what it looks like, what the current status is, and kind of what the cutting edge is, which is, you can see it's grayed out, but nonlinear perturbation theory. So Esteban asked me to talk about going beyond linear perturbation theory, and that is what the frontier of the field is right now, and it is what I've been focusing on really for the past 10, 15 years. So I'll talk about that a little bit, but it is getting very, very technical, so I won't go into many details. Okay, so basic idea, self force and waveform modeling. Okay, what's happening here? There we go. That. Okay, so again, just big picture reminder, and just remind you of the notation. Small object orbiting big one. In some of the figures, I'll use Q to denote the large mass ratio, big mass over small mass. So that's 1 over the small parameter I was calling epsilon, which was small mass over big mass. Now we're going to be focusing on the case where we have a background spacetime that's the Kerr geometry of the big black hole as if it were in isolation, and then small corrections coming from the orbiting secondary smaller object. And then we have an equation of motion. It looks like this for the motion of the small object, where this F1 is calculated from H1, F2 is calculated from H2 and quadratic combinations of H1, etc. And there's a very specific reason why I'm truncating these things at second order in the small mass ratio. So I will come back to that. Okay, but to motivate how we do all the modeling, I'm going to start with 0th order. It's the very simplest case. Here I'm going to ignore self-force. So now we're just talking about geodesics. We're talking about a test mass on a geodesic orbiting around a Kerr black hole. So you can see even in that scenario, it's a very complicated system. The orbit is, vastly more intricate than anything we see today in any context for any two-body system. It's much, much more complicated. But importantly, it is integrable. So if you think of theory of dynamical systems, which you may or may not have learned, integrable systems mean systems that have enough constants of motion that you can reduce the equations of motion to quadrature. So let me explain a little bit what I'm talking about. So we have a list of constants describing this two-body system. We have the mass and the spin of the large black hole. So little a is the spin. Then we have 3 constants of motion describing the orbit. We have the orbital energy. We have the azimuthal angular momentum. So if the spin axis of the big black hole is pointing up, and let's call that the z-axis, azimuthal angular momentum is angular momentum of the orbit around that spin axis. Then we have a 3rd constant of motion for the orbit called the Carter constant. And the value of the Carter constant tells you how inclined this orbit can get. Because what you're seeing here is that you have 3 kind of types of oscillation. You have the very simple periodic azimuthal motion, going the wrong way, this way, round and around the spin axis. That's one kind of phase of motion. Then if the orbit is eccentric, as it is here, you're moving between a minimum radius and a maximum radius. So that's another kind of phase of oscillation, going back and forth between minimum and maximum radius. Then you have polar oscillations going from a maximum inclination to minus that inclination, basically. So you're going up and down, up and down, up and down between some minimum and maximum. So associated with each of those phases, or each of those periodic motions, you have a phase that runs from 0 to 2 pi along each of those motions. So you have a radial phase, a polar phase, and an azimuthal phase. And you can define these phases so that they have constant frequencies, where the constant frequencies are specified by the values of mass and spin and energy, angular momentum, and Carter constant. Now, the way you make use of this is you say, okay, let's forget about just going back to the complicated geodesic equation and trying to solve for the position and velocity of the small body, of the test mass. Because the motion is integrable, we can transform to better coordinates. This is not coordinates on space-time. This is coordinates just describing the motion of the small body. This is parameterizations of the orbit. And so you can choose these 3 phases as coordinates, and then the constants of motion as other coordinates. So rather than position and velocity, you're choosing phases or angles and constants. And you can determine what this mapping is, what this transformation is. And so if you haven't learned dynamical systems theory or advanced Hamiltonian mechanics, these are called action angles. Well, specifically, okay, close enough to action angles, not quite action angles. These phi's really are angles, action angles in particular. These J's, the way I'm writing them, are not actions, but they're in correspondence with actions. So anyway, these are basically action angle variables. And what that means is I said each of these is constants. Each of these is a constant. And each of these phases has a constant frequency. So rather than a very complicated set of coupled equations describing the position and velocity, giving you this crazy motion, you have very, very simple ODEs. You have 3 phases with constant frequency, and then you have a bunch of constants. So you've reduced the complicated geodesic equations to very simple equations. This just tells you that phases are exactly linear in time, and these are exactly constant in time. So that's the geodesic case. That's the leading order case. Now, as soon as we turn on the self-force, as soon as we have a finite epsilon, things get considerably more complicated. Now, if you try to use those exact same coordinates that you were using for a geodesic, you get equations of motion that look like this once you turn on the self-force. You have the phases have this frequency specified by the J's. You then get corrections to them. These corrections are periodic in the phases, so that means the frequency itself now, the rate of change of the phase, is oscillating periodically. And then these things that were constant are no longer constant. They're now evolving with time at a rate that's proportional to your small mass ratio. And again, each of these terms on the right-hand side is oscillating. It's oscillating with the periods of the motion. Now, this is very bad for many, many reasons. One is, if you then want to actually solve these equations to get the orbit and eventually get the waveform, you need to resolve all these oscillations. So you're getting, some oscillation every period, and you're going through 10 to the 5 periods. And you have all this complicated beating phenomena, etc. So numerically, that's a disaster. You need super high resolution, many, many time steps, takes forever. And the other problem is that if you start off with this kind of formulation, we actually don't have a good way to solve the Einstein equations starting from this motion of the not this motion, this parameterization of the motion. So the fundamental problem here is that we are not cleanly separating oscillations from secular changes. Everything's all mixed up here. Everything's oscillatory. You haven't separated the timescales well. You haven't separated the short periodic timescale from the long timescale associated with the evolution of the binary. So what you do is you transform again, transform to better variables. So we started with just position and velocity, transformed to this phi and j. Now we're going to transform again to phi tilde and j tilde. And you can work out kind of the most nice choice of phi tilde and j tilde. Gives you equations like this. Where now the top equation is exactly what you had for the geodesic case. You've got the geodesic frequency, no corrections, no oscillations. But now this geodesic frequency is a function of slowly evolving parameters. So slowly evolving energy, slowly evolving angular momentum, etc. And so these J tildes, the energy, angular momentum, but I'm doing a transformation here, so it's not quite those things. I'm deforming those things. These new, nicely deformed, well-behaved things, they're slowly changing, order epsilon rate of change, but also they're only slowly changing. We do not have periodic behavior. There's no dependence on the phases anywhere on the right-hand side. So this has huge advantages. One is that it allows us to actually solve these equations very, very quickly, basically instantly, because you can take huge time steps because you only have slowly changing right-hand side. And as I'll mention in a second, this is what enables us to actually solve the Einstein equation in our case. Okay, so solving the Einstein equation, how are we going to do this? The fundamental assumption is that all the time dependence in these small corrections to the metric, these H1 and H2, all the time dependence is coming directly from small objects' motion and the black hole's evolution. So we're excluding anything happening that isn't on the very specific timescales of those two things, and having the periodicity, in particular, of the small object's motion. Exclude everything else. Then, rather than thinking of solving the Einstein equation on space-time, where you have metric perturbation that's a function of time and of some spatial coordinates, instead of that, we're going to throw away time and say, okay, now all the time dependence is a dependence on these things, the phi tilde and the j tilde. Then when you plug this ansatz into your Einstein equation, when you see a time derivative in the Einstein equation, you just use the chain rule. So you get derivative with respect to the first argument times a time derivative of that argument, which was just the frequency, omega, plus derivative of the second argument times the rate of change of that second argument. And what we then do is we replace this j dot with this expansion that we had here, which means this term comes in at order epsilon. It's suppressed by order epsilon relative to the first term. So at leading order, you're basically just seeing the periodic behavior. You're not seeing the evolution of your orbital system, of your binary. So once you've made this substitution, you then say that you're now going to solve the field equations actually on the phase space of the two-body system. You're going to get the metric perturbations as functions of phi and j. Forget about functions of time. You never specify the time dependence until you go back and solve these equations at the very end of the day. And these equations actually require as input for these capital Fs, actually require as input these solutions, Hn. So you're solving the coupled system, Einstein equations plus orbital evolution. You're solving the coupled system in this very particular way. And key thing here is that we are assuming that these H's are periodic in each of the phases. So they're inheriting the periodicity of the orbit. And that's critical because it allows us to solve the Einstein equations in this hierarchical fashion and ultimately generate waveforms instantly. Well, not instantly, very, very quickly. So I stressed earlier that you need accurate models in order to do gravitational wave data analysis. You also need fast models. You need to be able to generate models on a timescale of milliseconds or even faster than that. You need to, generate waveform templates on that timescale. And so the way we do that in Self-Force is using this offline-online split that's made possible through this particular treatment of the Einstein equation. So we said that the perturbations are periodic in the phases. That means we can just do a Fourier series in the phases with three mode numbers describing, the coefficient of each of these three phases. So then we've kind of removed the phase dependence of our metric perturbations. We can then solve the field equations on space, where we're just looking at the spatial dependence of these coefficients, these h and k's. So you solve for those things on a grid of j values. So you specify an energy, an angular momentum, a Carter constant. You then solve an Einstein equation to get the mode coefficients, the amplitudes, for that value. You then do it again and again and again and again until you've got these amplitudes all over the whole range of interesting energy, angular momentum, Carter constant, spin values. And from these amplitudes, you do two things. One is, well, you just evaluate this as distance goes to infinity, and that gives you directly your waveform amplitudes. So you store those. You just store your waveform amplitudes on a grid of orbital parameters. Then also from the amplitudes, you can compute those forcing functions that were appearing in the ODEs for the rate of change of the j's. So basically, at each point in parameter space, and sorry, these calligraphic j's should be j tilde, great, j tilde. You pick a point in parameter space, you solve for the amplitudes, you calculate these f's, capital F's, which means you're calculating the rate of change of the orbital parameters at that point. So at each point, you're basically solving a GR problem. So I don't know if you've learned Penrose diagrams, but this is a Penrose diagram of an object orbiting around a black hole. At each point in parameter space, you solve a GR problem. You're solving some form of Einstein equations. And then you're just storing the output. You're storing amplitudes at infinity, waveform amplitudes at infinity, and rates of change of orbital parameters. So everything is pre-computed and stored. So you have the waveform basically, except you don't yet know the time dependence of j or the time dependence of phi. But all the inputs for that are stored. Just go back to these ODEs. You've now stored the right-hand side. And so you can just solve those ODEs in a few milliseconds, and then just sum up all your modes, and there's your waveform. And so that can be done extremely quickly using this fast Emery waveforms package on a timescale of 10 milliseconds. And so really most of the community effort is now going into providing models for this package called Few. And this is the package that will be used by LISA, by the LISA mission internally for data analysis. Okay, so this is the overall construction, but anytime you're doing a perturbative expansion with some small parameter, you need to ask yourself, how high order do I need to go? And I mentioned I was specifically stopping at second order in all my expansions, and that's for a very particular reason. So if you go back to these ODEs, you can see that if you just change from t to epsilon t, basically just divide both equations by epsilon and make your new time parameter epsilon t, then you can see kind of by eye that you have a very simple asymptotic expansion for the solution to this equation for the phases. This is the asymptotic expansion. It starts at order 1 over epsilon, because basically each of these phases is growing roughly linearly in time. And so if you're waiting a time of order 1 over epsilon, which you are for a long inspiral, then the phase will also start at order 1 over epsilon. And if we've changed our time parameter to be epsilon t, then this coefficient is a function of epsilon t. This first term is called adiabatic order. Then you have all the subleading terms. This term here is called first post-adiabatic order, and you keep going on and on. Now, you can kind of just see by the scaling that if you've got this term correct, and you've got this term correct, that the error, whatever you're omitting, is small, because your mass ratio is, say, 1 over 10 to the 5. So your error in the waveform phase is going to be very small, and therefore not significant for data analysis. Where you're really trying to track very accurately is the phase. So the thinking for quite a while has been that in order to do LISA data analysis for Emery's, but also to use self-force models for anything, you really need these first two terms, and you don't need more for most applications. And so there's some recent work that I was involved in really showing quantitatively, doing data analysis studies showing that yes, these two orders are necessary and sufficient. You need them both, and you don't need any more, at least for Imries and Emrys. So this leading term that I mentioned is called adiabatic order, or 0 PA. This is fully determined by that leading forcing function and the rate of change of the orbital parameters. That's capital F0. That forcing function is fully determined by the dissipative first-order self-force, which is coming from a specific piece of the first-order metric perturbation. This next term, first post-adiabatic order, 1 PA, is fully determined by the next term, the subleading forcing function, F1. That forcing function requires the conservative piece of the first-order self-force, which means the full first-order metric perturbation, not excluding anything, and the dissipative piece of the second-order self-force, which is coming from a specific piece of the second-order metric perturbation, H2. You also get spin effects if your secondary object is spinning. They come in at first post-adiabatic order as well. So this is the motivation for stopping specifically at second order. We want what are called 1 PA waveforms with 1 PA accuracy, and that requires solving to get H2, second order metric perturbation, in order to calculate self-force F2, in order to calculate this 1 PA forcing function, capital F. What I'm skipping here is terms appear in between orders due to orbital resonances. So you get a half PA terms in between these two, entering due to resonances between these three different frequencies. So you have three frequencies, and when frequencies become commensurate, things that were oscillatory stop being oscillatory momentarily, and then you get an effect on your waveform phase that comes in at a half order between these. I'll say a little bit more about that later. Okay, so that's the overall picture. We want to solve second order perturbation theory, where we've got a black hole metric plus a first order perturbation plus a second order perturbation. We want to do that for generic orbits around a Kerr black hole. Ultimately, we want to do even more than that. We want to add environmental effects. We want to add beyond GR fundamental physics effects, etc. But just as a baseline, we need to do a minimum of that. Generic orbits, inclined, eccentric, second order perturbation theory. So first off, let's start at first order. 0 PA waveforms and linear perturbation theory before we get to second order. So in this field, there's a kind of dedicated community centered on the CAPRA conference that occurs every year. CAPRA conference has usually between 70 and 150 attendees, and it has focused on developing self-force and developing black hole perturbation theory tools and Emery modeling for the past almost 30 years now. And a huge focus had been on just first order linear perturbation theory up until the last 10 years or so. So we're trying to solve Einstein equation, and we're putting in this ansatz that we've got a Kerr metric plus a small correction. So you just expand this equation to linear order in epsilon, and you end up with a linear Einstein equation. Now, you may or may not have encountered this before, probably in gravitational wave theory that you were introduced to. You were looking at linear perturbations of flat spacetime, and you had a linearized Einstein equation for small corrections to flat spacetime. This is not that. This is small corrections to Kerr. So this operator on the left-hand side is very much not the flat space-time wave operator that you might be used to in linear gravitational wave theory. And it's more than just the ordinary linear operator. We are explicitly neglecting these rates of change of the orbital parameters and the black hole parameters. Because remember, I said we use the chain rule to figure out how time derivatives act on this H1, and these J dots come in with an order epsilon correction, so they do not appear in the leading order Einstein equation, they appear at next order. So here, this is almost an ordinary linearized Einstein operator, but it's neglecting some terms that go to the second order. And then you can rigorously prove that at this order, you can treat the small object, even if it's a black hole, meaning it's pure vacuum, still you can treat it as a point particle Dirac delta function in this linear Einstein equation. Then a whole bunch of tools and methods have been developed over the past 25 years to solve this equation, to get H1, to calculate the self-force from H1, etc. The common methods of solving the equation are you either just directly solve it, you just write it out, you choose a gauge that makes it look as nice as you can. If you haven't learned about gauge freedom in GR, don't worry about it. But basically, you can make some adjustments to how this equation looks. And that's one option. You just directly solve this equation. Another kind of more common option is you don't directly solve this equation. You act with another operator on this entire equation to get an equation for a different field, which is a curvature scalar. So you might have heard of the Weil scalars, psi 0 or psi 4, for example. Those are examples of curvature scalars that are constructed from derivatives of H1. And you can get nice, convenient equations to solve for those curvature scalars rather than this, coupled set of non-separable equations. And then if you need the full H1, you then reconstruct H1 from the curvature scalars through some process of integration and differentiation, depending on what exact formalism you're using. So there's a whole industry devoted to doing that. It's developed over the past 30 years. And this is kind of the state of the art where we are right now. This is the most generic that we've got. This is 0 PA accuracy. This is looking at a system like this. For generic orbits around a Kerr black hole, we don't currently actually have a fast, accurate waveform model that's fully relativistic. What we have is a very high order post-Newtonian and small eccentricity analytical expansion. So this is 5.5 post-Newtonian order and eccentricity to the power of 10. We have that for fully generic orbits around a Kerr black hole. You can see this is an example of the kind of waveform you get. And here it's being compared against a fully numerical, basically exact 0 PA, fully relativistic, non-approximate thing. And unless you zoom in, you cannot distinguish between them. But that's just on this scale. If you wait a long time, they will dephase, and this approximate waveform will not be sufficiently accurate for data analysis. Now, for a more accurate implementation, we have fully relativistic waveforms with no analytical approximations at 0 PA order for equatorial orbits around a Kerr black hole. That should be released publicly soon. Okay, then you can also do other interesting things even when you're restricting yourself to linear perturbation theory. For example, you can study resonances. So I mentioned that we've got 3 frequencies. These frequencies are now evolving with time because the orbital parameters and the mass and spin of the black hole are all evolving with time. So as they evolve, you can have moments where the ratio between 2 frequencies becomes rational. And in particular, you're interested in when the ratio between the radial frequency and the polar frequency becomes rational. So the azimuthal frequency kind of disappears from the dynamics, doesn't enter in. And it's really these 2 frequencies that are important. And when these 2 frequencies momentarily have a rational ratio, that's called a resonance, an intrinsic resonance. And things that had been oscillating, because they were oscillating with a linear combination of the 2 frequencies, things that were oscillating become stationary when this linear combination of the 2 frequencies becomes 0. And so things that had been kind of averaging out start accumulating while you're near this resonance. and that causes impact on the evolution of your system. Now here, this is plotting as a function of time, the three frequencies. So omega r down here, and omega theta, and omega phi up here. Here, this vertical dashed line, there's a resonance where omega r divided by omega theta is exactly 2/3. Now, if you look here, it looks like, well, nothing's happened. Where was this resonance? You can't see anything. You really have to zoom right in. And once you zoom in and you look at the impact of the resonance, you see this little tiny jump in the frequencies themselves. You get a little jump as the system sweeps across this resonance. So just for a sense of scale, if this is 10 to the minus 2, down here you're at 10 to the minus 6 or 7. So it's orders of magnitude smaller than the frequency itself, so it seems totally irrelevant. But the point is, you still have a long, 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 long time to evolve after that. So this little tiny shift causes a long-term change in the phase evolution. So you get actually multiple radians of phase difference between the case where you included the resonance correctly and the case where you just ignored it. So because this is such a unique signature, even if this is only a few radians, it becomes very, very important for data analysis because it's a very distinct signature of emeries. Okay, so that's kind of leading order or 0.5 PA type things. I skipped over secondary spin, but there's also a whole big effort in adding spin to the secondary object, which enters at 1 PA. It enters at 1 PA, but you can still deal with it in linear perturbation theory. So now let's go on to nonlinear perturbation theory, 1 PA waveforms. So let's back up to the Einstein equation. Now this has been my primary focus for the past 13 years. Formulating and solving the Einstein equation as second order in perturbation theory. So now we cannot neglect the second order term. We have a Kerr background plus epsilon h1 plus epsilon squared h2, some stress energy tensor describing the small particle. We expand everything out. We're using this multi-scale structure where rates of change of j, so j dots, get demoted by 1 order in epsilon. So when you organize the equations this way, you have the first order equation I already showed you. And the key thing there is that the particle was described as a delta function, which means it's localized in space, which means the right-hand side is 0 almost everywhere. It's non-zero only at the particle's position. That was the situation at first order. So you're dealing with actually vacuum, not just linear perturbation theory, but linear vacuum perturbation theory almost everywhere in space-time. At second order, that's out the window. Because when you expand this Einstein tensor, we're always told that GR is highly nonlinear, and that manifests itself by the fact that you don't just have a linearized Einstein tensor, you have a quadratic term in the Einstein tensor, you have a cubic term, etc., all the way up. So if you're going to second order perturbation theory, you have a term that's linear in H2. Let's put that on the left-hand side, and it's exactly the same operator as we had at first order. Now let's put everything else on the right-hand side and treat it as a source for the second order field. So we have some small correction to the stress energy tensor of the particle. Then we have a quadratic term coming from the expansion of the Einstein tensor that's quadratic in your first order field. Your first order field is non-zero everywhere in space-time. Well, except for, flukes where it happens to be oscillating through 0. Generically, it's non-zero everywhere in space-time. So you now have a source that's not just at the particle, it's everywhere, all the way up to infinity, all the way to the big black hole, all the way to the past, all the way to the future. And that is what makes formulating how to solve this very, very difficult. This source term right here, this quadratic source term. And it's actually not just difficult because it extends everywhere. And so it extends everywhere in particularly nasty ways, like kind of slowly decays with distance, and doesn't go to zero at the black hole horizon. But also, if you have a delta function sourcing your first order field, the first order metric perturbation is singular at the position of the particle. Just think of like a Coulomb field for an electron or whatever. Diverges as 1 over distance as you get, as distance goes to 0. And because of that, this source term over here, that's quadratic in H1 and involves derivatives of H1, this is very, very violently divergent at the particle's position. And it becomes a major challenge to even calculate it in a neighborhood of the particle. Now, in addition to that quadratic term, we also have a term that came from the J dot when we applied that chain rule. So that J dot is being replaced by the leading order forcing function, and you have a piece of the linearized Einstein tensor that's now proportional to the forcing function. And remember, we were applying a chain rule, so we have a derivative of H1 with respect to orbital parameters. So you get all these different effects at second order that you never had to worry about. Everything was very nice at first order. Everything's a disaster at second order. But at least in some scenarios, we've formulated how to do this, and we have done this and gotten complete 1PA waveforms. So solved the second order Einstein equation, pre-computed all the information we needed, and we can now generate 1PA waveforms in a few milliseconds for any choice of mass ratio and for any length of in-spiral, as long as it doesn't start too widely separated. Now here I'm showing you kind of the most generic thing we've got at the moment at 1PA order. In a very particular example where the mass ratio is 1 to 8, we have a small spin, so like a slow spin on the big black hole, and a very rapid spin on the small black hole. So this is the kind of thing we can currently model with 1PA accuracy. This is quasi-circular, so this is not the super complicated orbits that I showed you earlier. This is almost exactly circular, just slowly spiraling in. But everything works remarkably well in this simple scenario. So we don't actually have anything to compare against when the mass ratio is 10 to the 5, or even when it's 100 or 1,000. The only real benchmark we've got is numerical relativity, which is, basically as close to exact as we can hope for. And numerical relativity is only available for mass ratios of, equal mass up to 15, Q equals 15. So that's what we had to compare against. And so here in black is a numerical relativity waveform. And then in green is our 1PA waveform. And depending on your background, you might think, okay, well, who cares? Or you might think, well, this is insane. A model that was designed for extreme mass ratios is actually incredibly accurate until a few cycles before merger, even for mass ratio 1 to 8, even for a rapidly spinning body. So this was the outcome of many years of labor, and this is kind of the frontier of the field. But I'll show you one more thing, which is complete in-spiral merger ring-down models. So self-force-based models are very different from the current waveform modeling paradigm for several reasons. One is, as I mentioned, the models are fast to begin with, whereas for LIGO, Virgo, Cagra models, historically you would have a very, very slow, accurate model, numerical relativity, and then you would build some interpolating model or some effective phenomenological model or something that tries to reproduce as well as possible numerical relativity. And very often, even that model is not fast enough. And then you have a more a less accurate, more efficient model that tries to reproduce the intermediate model. So you have this whole layer of trying to make things fast enough. For self-force, you don't have that. You have a model where the first principles model is already fast. Now, the second big distinction between self-force modeling and the kind of standard paradigm of ground-based detectable signals is that the nice analytical or semi-analytical model to start with for LVK signals is post-Newtonian theory. And post-Newtonian theory does not deal with the strong field. It does not deal with the merger. And so, if you think back to the beginning, I showed this picture of a typical signal that looked just like this, but you had to use 3 different models to describe it. You had post-Newtonian theory, numerical relativity, and then black hole perturbation theory. With self-force, you get all 3. You don't need to add anything in addition. So this was a plot generated by one of my postdocs, Lorenzo Kukler. Master ratio 1 to 10. You can see that currently we are not accurate enough to use this for actual data analysis, but that's okay. We don't want to model systems with this mass ratio. Well, that shouldn't be the primary aim. We're focusing on smaller mass or larger Q. So say if we observe a signal with mass ratio 50 with a ground-based detector, that's what we would hope we would have a very good model for. Okay. So I'll just start wrapping up and just remind you of the overall storyline here. So historically, up until now, the scientific endeavor of gravitational wave astronomy and the scientific endeavor of solving the two-body problem and modeling gravitational waves has all focused on nearly comparable mass binaries. But asymmetric binaries actually have a very unique place in gravitational wave astronomy. They provide you with very unique information and in often cases much more precise information than you can get from other systems. So in particular, with asymmetric binaries like EMRIs, you can get high precision probes of black holes. You can learn about the nature of black holes, precision probes of galactic cores, measurements of fundamental physics, etc. Then the way we model these systems, currently the most viable method is using self-force. Actually, I'd say the only viable method for EMRIs is using self-force. Or you can cook up another model that's kind of trying to replicate self-force. This has several interesting features. One is, as I tried to emphasize, kind of a connection to the basics of GR, that what we're calculating is a correction to the equivalence principle. Small corrections to this notion of everything moving on geodesics. We also just saw in those last few slides that self-force model appears to be very, very accurate, even for mass ratios that are 1 to 5, 1 to 10. And going back to this story of GR being highly nonlinear, you might think, well, okay, it's not that highly nonlinear because there we are not doing a super high order perturbative expansion, and we're getting most of the signal very, very accurately. And unlike most waveform models, self-force by itself comes with a fast waveform generation mechanism. Now, the overall status is, well, we've done a lot of exciting results, but there's still a long road to getting the ultimate goal, which is 1 PA accuracy for waveforms for generic orbits around a spinning Kerr black hole. And the timeline of Lisa says we want to have that ready to go actually by 2032, which is frighteningly near considering it took me and my close collaborators almost 10 years to do this for quasi-circular orbits. Okay, now just as an advertisement to you all, if you're interested in this field, getting involved in this field or doing a PhD in this field, there's a few good resources. So there's an introductory review article that I wrote with Lior Barak. That's really aimed at students starting their PhD. It's a little bit out of date in terms of the latest results, but it still gives you an introduction to the concepts. Then if you really want to get into the field, there's a very advanced overview of the whole subject that I wrote with Barry Wardell a few years ago. And besides just papers, there's this amazing resource called the Black Hole Perturbation Toolkit. It's just open source software. It will actually do a lot of those things I showed you. So for example, there's the Kerr geodesics package, which allows you to just to study Kerr geodesics. You just pick the parameters, out pops the geodesic, you can look at it, make movies of it, etc. You can look for resonances, you can do all kinds of science just with Kerr geodesics. There's a perturbation equations package that you can use to get actually all the Einstein equations, all the Tucholsky equations, etc. There's the Tucholsky package, which will actually solve the Tucholsky equation for you at linear order with a point particle source. And this package I kept referring to, fast damping waveforms, this is actually a publicly available package you can use to actually study the waveforms themselves and do data analysis. Okay, I will end there. Thank you all for listening. And I think we've got a bit of time for questions.